Jai Hind students. Today I am going to discuss some numericals on the topic time response analysis. So the first numerical here is the forward path transfer function of a unity feedback control system is given by GS is equals to 2 upon S into S plus 3. Okay. Obtain an expression for a unit step response of the system. So here what we have given, they have given to us, that is GS is equals to 2 upon S into S plus 3. So you can see here it is a closed loop control system which is having a unity feedback. Okay. So we can, as we know, the transfer function of a closed loop control system with unity feedback will be CS upon RS upon GS upon 1 plus GSHS. So GS is given to us here, and HS will be 1 since it is a unity feedback system. So we will put the values of GS and HS in this equation and we'll calculate the, first of all, the transfer function of the system. Okay. So the transfer function will be 2 upon S into S plus 3 upon 1 plus 2 upon S into S plus 3. So while solving, we will get cancel out, this will S upon S plus 3 will cancel out and we'll get S square plus 3S plus 2. So this will be the value of transfer function, right? Now we have to calculate the output, that is the response of the system for a unit step input, right? So that means RS will be here, since the input is unit step input, then RS will be equal to 1 by S. So we can put the value of RS in this equation. So we'll get CS will be equal to 1 upon S into 2 upon S square plus 3S plus 2. Okay. Now what we have to find out the CT. Okay. So we can do this S square plus 3S plus 2 can be written as 1 upon S into 2 upon, we can write it as S plus 1 and S plus 2. S square plus 2 and this will be 3S. Yes. Now by using partial fraction, we will find the value of CS properly. That is, CS will be equal to A upon S plus, let's say, B upon S plus 1 plus C upon S plus 2. Okay. First, we will calculate this value of A, B and C from here. So it is coming out to be, when we solve this equation, value of A will be 1 and C also it will be 1. For B, it will be minus 2. So we will put these value in the above equation. We'll get CS is equals to 1 upon S minus 2 upon plus 1 upon, what was it? S plus 1 or S plus 2? Minus 2 upon S plus 1 and this will be S plus 2. Okay. Now, taking inverse Laplace transform of this above equation, we will get the value of CT, that is the time response of the system. Taking inverse Laplace transform of above equation, we will get the value of CT, which will be 1 by S can be written as 1 or UT minus 2 into 2 is a constant. So 2 into 1 upon S plus 1, 1 upon S plus 1 will be equal to e raised to the power minus t plus 1 into e raised to the power minus 2t. You can directly write it as into UT. So this will be the time response of the system which is given to us in the previous question. Now coming to the next problem, here we have to find out the time domain specification of the closed loop control system which is having a transfer function this 4 upon s square plus 2s plus 4. And when the unit step signal is applied as an input to this control system. So what were the time domain specifications? Those were what I have discussed in the previous lecture, were rise time, right? And that was peak time and the settling time, the peak overshoot, natural frequency, damping frequency, and what else we can write as the damping ratio. So we'll calculate all these values one by one from this transfer function. So first of all, though, I'll write the value of the transfer function here, that is 4 upon s square plus 2s plus 4. Since we know from this transfer function, we can conclude that it is a system, second order control system. So we have the standard formula for the second order control system comparing with the standard sum transfer function above equation, okay? Which is the standard transfer function is omega n square upon s square plus 2 zeta omega n plus omega n square. So when comparing equation 1 and 2, what we will get from equation 1 and 2, we'll get the value of omega n square is equals to 4, which come out to be omega n is equals to 2, as we will neglect the negative value of the frequency, natural frequency. So it is coming out to be 2 radians per second, okay? And while comparing this equation, this term with this term, we'll get 2 zeta omega n will be equals to 2, okay? So it is cancelled out, and with zeta is equals to 1 by omega n. It is coming out to be 1 by 2 is equals to 0.5. This is 0.5. Okay. So we have calculated the value of zeta and omega n. Now we can calculate the value of omega d. And this is zeta. Omega d will be equal to omega n under the root 1 minus zeta square. So omega n we have 2 and this is 1 minus 0.5 ka whole square. So this is with the value of omega d, which is coming out to be, we can calculate it as 2 into 1 minus 0.25. That means it is 0.75, and the value come out to be, the value is 1.73. The value of omega d will be 1.73 radians per second. Okay. Now we will calculate the value of, we have the value of omega d, omega n. We have, I'll write for reference, I'll write the values here. We have omega n is 2, omega d is 1.73 and zeta is equals to 0.5. Now next we can calculate the value of rise time. First of all, we'll calculate the value of phi, which is tan inverse under the root 1 minus zeta square upon zeta. Okay, so we can write as tan inverse under the root 1 minus zeta is 0.5 whole square upon 0.5. So while calculating this value, it is coming out to be, phi is coming out here, pi by 3. Okay, now we can calculate the value of, first of all, TR. Rise time is pi upon omega d. Okay, so pi here is pi and omega d is 1.73. So it is coming out to be, so TR is coming out to be 1.20 seconds. Okay, and similarly for TP, we will have the formula is pi minus phi upon omega d. We have the value of phi as pi minus, this is pi by 3. And what is value of omega d? Omega d here is 1.73. So while calculating, we have the value of TP as 1.813 second. Okay, now TPTR settling time. Okay, let me find out the value of settling time. For 2% tolerance band, it is 4 upon zeta omega n, right, for 2%. Since nothing is given in the question, we will take as 2% tolerance band. Okay, so it is coming out to be 4 upon TS will be 4 upon zeta, we have 0.5 and we have omega n as 2. So it is coming out to be, sorry, this is 0.5 now. It is coming out to be 4 seconds. Okay, now last is the peak overshoot value. Peak overshoot value will be, if we talk in percentage, the value of peak overshoot is e raised to the power minus pi zeta upon under root 1 minus zeta square, okay, into 100. So we will put the values here. E raised to the power minus pi into zeta is 0.5 upon under the root 1 minus 0.5 whole square into 100. So after solving this, we will get the value of MP as, while solving this, we will get the value of, I'll write once again, e raised to power minus pi into 0.5 upon under the root 1 minus 0.5 whole square into 100. So we will get the value of MP as 16.32%. You have to simply put the values here and you will get the values. So these are the time response specification for the second order control system. Now I would like to, so these you can see I have just write down the formula and put all these values here for simply showing the actual values for rise time. You can also calculate the delay time, though which we have not covered in this numerical. So delay time will be 1 plus 0.7 delta zeta upon omega n. So we can put the value of zeta, that is 0.5. So it is coming out to be 0.675 seconds. Okay, and all the values rise time, that is pi minus phi upon omega d. Here theta is nothing but it is phi. So that comes out to be 1.20 second. And for peak time, it is pi upon omega d. So we will put the value of omega d, which is 1.732, and TP comes out to be 1.813. And for peak overshoot, the value is e raised to the power minus pi zeta upon under root 1 minus zeta square, okay, into 100. So when we'll put the values of here from delay time, this is the delay time. Delay time is the time where the formula is 1 plus 0.7 delta upon omega n. Delta is nothing but it is zeta here. We have used here zeta word. We'll use zeta over here. So these are the formulas that we have used in the previous numerical, and these are, I have shown here just the formulas, and putting the values will get these final values which I have described in the previous slide. So we have not done the value of delay time, which is 1 plus 0.7 zeta upon omega, and this delta is shown here, but it is zeta, okay. And similarly, this pi theta is pi here, okay. So we can find out the value simply by putting the value of zeta, which is 0.5, and simply by putting the value of omega n, which is 2, we'll get the value of delay time, which is coming out to be 0.67 seconds. And for the rise time, we have pi minus phi upon omega d, and the value of phi is already calculated, which is coming out to be pi by 3, and pi minus pi by 3 upon 1.732 will give us the value of rise time, which is 1.20 second. And for the peak time, the formula is pi by omega d, and while putting the value of omega d, which is 1.732, we'll get the value of TP, which is coming out to be 1.813 second. Now for peak overshoot, the formula written here is e raised to the power minus pi zeta upon under root 1 minus zeta square. So I have put down the value of zeta, which is 0.5, and it is coming out to be 16.32 in percentage. Okay, and for settling time for 2% tolerance band, which I have taken in the previous slide as well, so it is 4 upon zeta omega n. So when I'll put the values here, 0.5 and 2, will get the value of settling time, which is 4 seconds. Okay, so I'd like to describe one more example based upon the these values. So based upon the second order time response. So the question given to us is second order control system is given to us, which is containing this numerical. So let me take the values from the book. RS, this is 20 upon S plus 1 into S plus 5. Okay, so this is the question, 20 upon S plus 1 into S plus 5. Let me. Okay, and this is again a unity feedback control system. Here RS is input applied to this system and CS is the output. What we have to find out here, we have to find out the value of the characteristic equation. Here we have to find the characteristic equation. Okay, this is the numerical that I have taken from a book. That's why I am looking downwards. So we have to find out the characteristic equation, and we have to find out the value of natural frequency, damping factor, damping ratio, right? We have to find out, we can also find out the value of, MP, okay, rise time, settling time, and that was peak time. What else we can find out? Okay, okay. So these are the values that we need to find out. So from this diagram, from this block diagram, first we have to find out the value of the transfer function. So you can see here, this block diagram given to us will be called as the GS. This is the gain of the forward path transfer function. CS is the output here, RS is the input, and the RS here is the unit step input, right? So first of all, we will find out the value of the transfer function for this particular block diagram. So this is CS upon RS will be equal to, we know the formula, GS upon 1 plus GSHS. Okay, then while first we find out the value of the transfer function, then we'll compare it with the standard transfer function. By comparing, we'll get the value of natural frequency and the damping ratio. Then once we get the value of natural frequency and the damping ratio, we will calculate the value of natural frequency and damping ratio. We will calculate the value of damping frequency, and we can also calculate, we are also able to calculate the value of peak overshoot. Okay, and similarly, we can also calculate the value of rise time and the settling time. Since nothing is given to us, we can calculate the value of settling time for 2% tolerance band. Otherwise, if in the question, it will be mentioned if we are required to calculate the value of settling time at 5% tolerance band. Since nothing is given here, so we'll calculate at 2% tolerance band. So first of all, we'll go for this. Since it is a negative feedback system, we'll use 1 plus GSHS. Okay, so we'll put the simply we put the value of CS upon RS. Simply we put the value of GS, which is 20 upon S plus 1 into S plus 5 upon 1 plus 20 upon S plus 1 into S plus 5. So let me do the calculations here so that it may be, I'll feel comfortable. Otherwise, the slide change, so there is I'll get some difficulty in calculating S plus 5 plus 20. Now 20 upon S plus 1 into S plus 5 upon. So here CS upon RS is 20 upon S plus 1 into S plus 5 plus 20. Now I can easily calculate here 20 upon, this is S square plus, this will become 5 and this will become 6S plus 5 plus 20. Okay, so I will write down the value as S square plus 6s plus 25. So one point to be kept in mind here from this equation, that the value from the standard transfer function, we have the standard transfer function as 20 upon s square plus, omega n square upon s square plus 2 zeta omega ns plus omega n square. So you can see here we have two different values. Okay, so we cannot change this value. So what we can do is we can multiply the numerator and denominator by 25 so that we will get the same value, and this of the omega n, and now this 20 upon 25 will become the constant k, right? So we can also, this 5 4 ja 20, this is 5 5 ja 25. So what we have here is Cs upon Rs will be equal to, why I am doing it? So that I can easily compare it with the standard transfer function. While comparing this value with the standard transfer function, okay, while comparing this value with the standard transfer function, I will get the value of omega ns and omega n square is equals to 25, and 2 zeta omega ns will be equal to 6s. Okay, and now the characteristic equation for this question will be, characteristic equation from here will be, what will be the characteristic equation? Characteristic equation will be the denominator of the transfer function when we will equate it to 0. So characteristic equation will be s square plus 6s plus 25 is equals to 0. So this will be the characteristic equation. And when we'll compare this value, let me write this equation 1. Now comparing equation 1 with equation 2, okay, so with equation 2, which is Cs upon Rs will be equal to omega n square upon s square plus 2 zeta omega ns plus omega n square. We will get the value of omega n square is equals to 25, and value of 2 zeta omega n will be equal to 6. So from here we get omega n is equals to 5 radians per second. Okay, and we will put the value of omega n in this equation. We'll get value of zeta, which is 6 upon 2 into 5, which is 3. So value of zeta is coming out to be 0.6. Okay, so omega n is 5 radians per second and zeta is 0.6. So now we can easily calculate the value of damping frequency, which is omega d is equals to omega n and under root 1 minus zeta square. Okay, so it will be 5 into under the root 1 minus 0.6 whole square. So it is coming out to be the value of omega d will be 4 second. While solving, after solving, we will get the value of omega d as 4 radians per second. Okay. From also we can find out, since zeta is known as the damping ratio, we can also calculate the value of damping factor, which is zeta into omega n. Okay. Now I'll calculate the value of the rise time, which is pi upon omega d. And what is the value of omega d here is pi by 4. Okay, so this is coming out to be, let me check, and for peak time this will be pi minus pi upon omega d. Okay, first we will calculate value of phi, which is phi is equals to under root pi is equals to phi will be tan inverse under the root 1 minus zeta square upon zeta. Okay, So it is coming out to be 10 inverse under root 1 minus 0.6 का whole square upon 0.6. Okay, so I'll calculate this value. Let me just give me 1 second. And for settling time, I will write 4 upon zeta omega n. I will calculate all these values. First, I'll write the formula. I will write down the values directly. 0.6 into omega n. What was the omega n? Omega n is 5. Okay, 5. So into 10. So it is 2. So it is 3. This is 4 by 3 second. Okay. Now the value of phi here coming is, so while calculating the value of TR, which is pi by 4, it is coming out to be 0.78 seconds. Okay. Now we can calculate the value of phi, which is 10 inverse under the root. This is coming out to be 1.36 upon 0.6. So it will be coming out to be 0.64. That means 10 inverse of 0.8 upon 0.6. It is coming out to be, the value will be 1.33. Okay. So, sorry, while solving, the value will be 53.06. Okay, phi is 53.06 here. We can write down here 06. Okay, and now when we put this value of phi here, TP will get pi minus 53.06 upon omega d, which is 4. So TP is coming out to be 0.55 seconds. Okay, now we can calculate the value of MP. So we know the value of zeta here is 0.6. Okay, and so MP also we can write here. We can calculate the value of MP from this equation. From this equation, we can write the value of MP. I can calculate here. MP is equals to e raised to the power minus pi into 0.6 upon under the root 1 minus 0.6 का whole square into 100. So the value percentage MP is coming out to be 9.4%. So I have in this lecture I have covered 3 different numericals. And first we have to find out simply the expression in time domain, output response of the system in time domain. In the second example, I have tried to calculate the values of these natural frequencies, the time domain specifications with the help of the transfer function is given to us. And in the third diagram, in the third numerical, the block diagram is given to us, and I told you how to calculate these specifications, how to find out the value of the characteristic equation, and we can also calculate the value of the response if input is applied to us. So it's just like when the input applied to the system is given to us. Just like in this example, you can see the step input is given to you, right? So you can, since you have the value of this CS upon RS, so CS can also be calculated since RS is 1 by S. So finally, by taking inverse Laplace transform, CT can be found out. So that's all for today's lecture. Thank you.